Hello, welcome to the first lecture. This is the first lecture. This is Chemistry 161 with the University of Hawaii. So that's first semester general chemistry. Okay, so this is a chemistry class. Figured a good way to start chemistry is to define chemistry. Chemistry is defined as a study of matter and its changes. We'll get into this a little bit more. But before I get into that, let me talk to you about a very dangerous chemical. That chemical is dihydrogen monoxide, also known as DHMO. DHMO is a very powerful greenhouse gas. It's projected to cause about 80% of the global warming. It is on the order of 500, maybe more times more powerful of a greenhouse gas than carbon dioxide. It was used in the Fukushima nuclear power plant before it exploded. We find it in cancer cells. We use it in animal research, and there's been a huge investment for the use of this chemical in warfare. So there is actually a website that says ban DHMO. And if this is my attempt to hook you, DHMO, dihydrogen monoxide, is in fact water. And everything I've said here is true. It is a greenhouse gas. It is the primary greenhouse gas for the Earth. If it wasn't for water vapor, the Earth would be much, much cooler than it is now. And the whole idea behind climate forcing is that carbon dioxide is a very weak greenhouse gas, but it evaporates more water, which will cause a global warming. So, and nuclear power plants, they use water. Water's found in all cells. You certainly need water in animal research. And if you ever heard of the Navy does use look at how water can be used in warfare because they float their ships on it, right? So everything I said was true. And it's the idea here is like, oh, so you can spin things in a certain way to make things look really dangerous. And you can use the word chemical. Like, what is a chemical? It's something that's made of atoms, right? So everything, at least that we care about, at least that I care about, I don't care so much about neutrinos and stuff. That's not a chemical. But most of what we worry about, touch, feel, smell, breathe, these are all chemicals, and the chemical has a negative connotation. So, ban DHMO. Okay. So let me move on. And this is the first chapter. So, in the first couple chapters, we are going to jump around topics like crazy. So, hopefully, you can keep up. You can always pause the video and return and look at things a little bit more. Okay, so science. What is science? Science is a systematic approach to solving problems. And specifically, we use the scientific method. And the scientific method is that systematic approach that science uses. And when you say science, we usually mean natural sciences, not necessarily social sciences. Social sciences, and there's nothing wrong with social sciences. They're a very interesting type of field of study. But the one thing about natural science is that we can control the variables much more than we can in human interactions. So, and specifically when I say sciences, there's the top three. These are the most broad. Biology is the study of life. Physics is the study of the physical world, which is a circular argument. To me, it's forces. It's how long the vector is and where it points. Chemistry is the study of matter. So matter we'll talk about soon. It is something that has mass and volume. And there are types. The types of chemistry are synthetic, physical, and biological. So synthetic chemistry, these are the chemists that actually make things. This is what most chemists are. Then there's physical chemists that are kind of the physics of chemistry. That's what I am. I'm a physical chemist, and most physical chemists, general chemistry is usually taught by physical chemists. Organic chemistry and inorganic chemistry is considered synthetic chemistry. Like for me, when I did chemistry, it was with lasers and vacuum chambers. So that's more of the physical realm. Also, computational is considered physical. Nuclear chemistry is also considered physical chemistry. Now, an emerging field is biological chemistry, so biochem, biological chemistry, these kind of things. This is a more an emerging field, and it used to be part of synthetic, but now it's got its own sort of branch. Okay, let me go back to scientific method. And the scientific method, well, let me talk about a few terms here. So, start with observation. So when you're performing the scientific method, observations, two types: quantitative or qualitative. So a quantitative is a number-based observation, and qualitative is an idea-based. So quantitative would be like there are 20 people in the cafe. That is a quantitative observation. Qualitative idea is this cafe is busy, or this cafe is not busy. That's an idea-based observation. And we can skip much of the scientific method to go with a scientific law. Scientific law is a summary of observations. So, a summary of observations. So, something like the law of conservation of mass. That is, matter is not created or destroyed in chemical reactions or physical processes. So, that's the law of conservation of mass. Matter is not created or destroyed. We've observed that. And can scientific laws be broken? Yes, they can. Laws can be broken, but usually under specific circumstance. The law of conservation of mass is broken in nuclear reactions. So what have we done though? We've changed the law. We said, all right, well, matter is not always conserved because of nuclear reactions. So, or you can turn energy into matter in like high energy colliders. So why don't we instead say that change the law of conservation of mass? Say it only applies to these circumstances. So that's also scientific method because we see something and we tweak it. Okay, let me go back away from voice of law. So observations. Once an observation forms, you can come up with a hypothesis. The hypothesis is an educated guess. Then experimentation tests the hypothesis, and once the hypothesis is confirmed or a series of hypotheses are confirmed, then it becomes a theory or a proven fact. So let me give you a couple of ideas with this. So let's say that you're applying the scientific method to your car not starting. So you try to turn on your car and the car doesn't start. Well, you're like, all right, well maybe I'm out of fuel. So that's your hypothesis. The observation is my car won't start, and I'm going to hypothesize, oh, I need more fuel. So you put more fuel in the car, and the car still doesn't start. Like, all right, well, I've confirmed now that the lack of fuel hypothesis is incorrect. Maybe my car's battery is dead. And then you get a friend to jumpstart your car, and the car starts. So now your hypothesis of a dead battery has been confirmed, and it can be the theory. You've proven the theory of why my car won't start due to the dead battery. Of course, this is a very small example. Theories can be much bigger. Things like atomic theory or germ theory. So one thing, theories can be and often are wrong because we learn more, and we can either tweak the theory or we can just throw it out completely. And right now, with our current understanding, we have two theories of science. So we have quantum mechanics and we have general relativity. Those are the main types of theories describing the world the way it is. So this needs to be, so that's a scientific theory though. So scientific theory of quantum mechanics and general relativity are true. So then you have string theory. String theory is an example of a theory that's not a scientifically proven theory. So string theory, it's proven, but it's proven mathematically. So it really should be the string hypothesis, but it is commonly called string theory. String theory is not experimentally verified, and that's one of the difference between contemporary science and like ancient Greek science, or basically anything before the 19th century. String theory would be perfect for Greek philosophy because it's a beautiful theory. It's very mathematically sound. But in contemporary science, we need experiments. Scientific theories are experimentally based. But theories often are wrong, and it may not necessarily be a problem with the theory. Maybe the theory needs to be tweaked a little bit, or maybe the theory is just completely wrong. So we're going to cover two theories in this class: Lewis theory and valence shell electron pair repulsion, also known as VSEPR. Those are two theories, and they're wrong. We know that they're wrong, but we still use them because they work really well. But they only work. They have their limitations. but it's just they make so much sense and they're so easy, we still use them. So even if a theory is wrong, doesn't mean it's not usable. But Another theory that is mostly right but sometimes wrong is germ theory, the idea that pathogens cause illness. Not every illness is caused by a pathogen. Cancer, or some people have argued that some cancers may be from pathogens, but certainly some types of cancer are not from pathogens. So, like, well, then but germ theory says that illness comes from that. So heart disease is another disease that you can that's not explained by germ theory. Does that mean germ theory is wrong? No, doesn't necessarily mean that, but it has its limitations. So, okay, so we just have to tweak the theory. So theories can be and often are wrong. Laws can be broken, and science is tentative. This is a big thing that people don't sometimes forget. Once something is proven, so if string theory is proven to be correct, that means that's it. Or if something happens where general relativity turns out to be wrong, so classical physics, Newtonian physics, that was proven to be wrong due to observations with the orbit of Mercury. And once the orbit of Mercury was found out that to follow Einstein's model rather than Isaac Newton's, then we got rid of that theory. So science is tentative and it's experimentally based. Experimentally is what verifies it. So Einstein's theories of relativity were not considered valid until we had an observation that could prove one and discount the other. So models and simulations are not considered to be valid for natural sciences. So that's why I say string theory is not a valid scientific theory. Also, another thing, correlation does not mean causality. So this is a very common mistake that people make. Correlation does not mean causality. Sometimes there might be a common third factor. Sometimes it's chance. There's lots of things that they correlate that do not necessarily are linked. A famous one was that polio outbreaks seem to correspond with ice cream sales. So when polio, before there was a vaccination for it, there was a push saying, stop buying your kids ice cream, they might get polio. And it wasn't the ice cream that caused it. It was the fact that in the summertime people mix more, so it's the contact with other children and was causing the polio outbreaks, not the ice cream. So what they had in common, of course, was the warm temperatures. So that's an example of a common third factor. So correlation does not mean causality. So basically, if someone says this correlates that, what they're really saying is, I'm not having a scientific discussion with you. But at the same time, science is powerful. Science is very powerful. It can put people to prison. When people say it's scientific, there is some power with that. And with that, bad science can severely injure people. There was this science, and I hate using the word science in this case. There was a science called eugenics, and eugenics is the belief that there's different races of humans. Of course, this is complete and utter hogwash. I mean, there is only one race of human, and that's the Homo sapiens, right? So and races are a little, like, a biological species is a little fuzzy, because if you have two members of the same species, if their offspring is fertile, then they're considered to be part of the same species, but of course species evolve. And you have certain types of mixes, like lions and tigers, they can produce fertile offsprings, and obviously humans have fertile offsprings with Neanderthals, because according to 23andMe, I got some Neanderthal genes in me too, so many of us do. So, but anyways, let me go back to the idea. Eugenics was that there's different races of humans, and if they're allowed to interbreed, will cause the extinction of the human race due to inferior genes. And this is literally Nazi science. It was really that the Nordic race was the and I races. I if you know I'm Nordic actually. I'm blonde haired and blue eyed, and but I can tell you as apparently the most advanced human according to the theory of eugenics. I can tell you that it's complete hogwash. It's not true. There's nothing about me that's superior or inferior to anybody else, except for my taste in music, which is that of about a 14-year-old by what I listen to on the radio. But besides that point, there is nothing as far as a race of humans that one is superior to the other. We're all the same race. You could maybe argue that there's different subspecies of humans, so regional adaptation, but it doesn't fit the model either because we intermix so much. So we're not like African lions versus Indian elephants versus African elephants, or Sumatran tigers versus Amur tigers. Because humans, we just intermix so much, it doesn't really fit for that anymore. But I mean, anyways, so I told you, this upsets me. I really think the whole idea of racism, and I hate when people say, "Well, what race are you?" I'm like, human. But what people probably mean is nationality. I mean, like I was born in the Philippines, or I was born in the USA, but my ancestors came from Scotland. So that's probably what they mean, but we use the word race because of this stupid theory. But anyways, people really believe this, and some people still believe this, that if you intermix the races, we will cause the end of the world. And we in the United States, we sterilized about 300,000 women in Puerto Rico. So this is because of eugenics. So we've done some bad things. And let's talk about bad science. Bad science uses correlations, relies on models instead of experimental data. And one thing that's really important for bad science is consensus. Consensus is completely irrelevant. So I talked about Einstein before. Einstein was and is extremely popular in the United States. We loved him and we still love him. Where people hated Einstein. I'm not sure if they still do or not, but they hated Einstein in Europe. Like, I mean, he was a German-born Jew, and the Germans hated him because he was Jewish, and the English hated him because he was German. So you had this German-born Jew who came out and said, "Hey, you know what? That Isaac Newton is wrong." So people were really upset. They're like, "Get Einstein out of here." In Germany there was like something like 1,000 scientists or something like that, or a million. I don't know. It was a 10,000 or something like that. 10,000 scientists against Einstein, and Einstein famously said, "It would only take one." And Einstein's point was, it doesn't matter how many people think something, it's about what the data says. So science is experimentally based. It's not a vote, it's not a consensus. We all think this way, so it must be true. Nope. No, everyone can think that malaria is caused by bad air, in which they did think that. But malaria, of course, is a vector disease caused by mosquitoes. So consensus is irrelevant, and it's a very commonly see this in bad science. Okay, so pretty much everything I'll talk about this class. What's nice about this class, Chemistry 161, is it hasn't really changed since about 1960. And this course has been taught pretty much the same way since Linus Pauling wrote the textbook on it. And each subsequent textbook is about the same. We have prettier pictures now, and of course online content, which you will learn to love as this semester goes on. But everything we talk about in this class is pretty solid science. It's not something that this is not an emerging field, right? So like the number of planets that we have in the solar system, this is an emerging field. We think that there's a ninth. And sometimes we thought we changed the definition of planet and Pluto was out, right? So that's something that's kind of an emerging field. Astronomy is a very big emerging field, for instance. But chemistry, at least at this level, is not an emerging field. So everything here is very very objective. So, okay. So I mentioned chemistry is the study of matter and its changes. So chemistry is the study of matter. So let's talk a little bit about matter. And let's talk about the states of matter. So 3 states: solid, liquid, and gas. So a solid has a defined shape and a defined volume. So your textbook is a solid. It has the shape of a rectangular prism and it has a set volume, probably about on the order of 1.5 liters. I'm looking at my textbook right now. Of course, you're doing you probably do the IDAP thing, but if you had the printed version of it, like I do, it is that shape. That is a solid. A liquid is has an undefined shape but a defined volume, or indefinite shape but a definite volume. So liquid water is an example of one. So I can put water in a glass. I can put it in a vase. I can put in a bottle. I can turn a bottle on its side. The shape is going to change. It's going to change to the shape of the container. But one thing about water, a liter of water has the same volume if you put it into a large vase, if you put it into a bucket, the volume doesn't change. Does the liquid change a little bit? Like, well, yeah, if you heat it up, it tends to expand. Water is densest at about 4 degrees Celsius, but so the volume can change slightly with temperature. But generally speaking, when you're making something in lab and you put 20 milliliters into a graduated cylinder and you put it into a beaker, you're not thinking, gee, is the volume going to change? No, the volume of the liquid is not going to change, at least not appreciably. Okay, and then gas. Gas have neither set shape nor a set volume. So air is an example of a gas. So if you have a tire, what's the shape of the tire? The tire is the shape of the donut that's in the air or that's in the tire. What's the volume? It's the volume of the tire. What happens if you take a tire into an empty room and then you slash a tire? What happens to the gas? Well, it's now the volume of the room, size of the room, right? So gases have neither a set shape nor a set volume. And some people say, what about plasma? Plasma is an ionized gas. It means you have one or more of electrons ripped off of the gas, and we will consider plasma to be a gas. So if you're wondering where plasma fits in, if it fits in the state of matter. And another thing about gases are compressible. Liquids are not compressible, and if you've ever gotten air in your brake lines, you know that your brakes don't work very well because your brakes are a hydraulic line, and the idea behind a hydraulic is when you put force on a liquid, the force carries through the entire liquid. So that's why if you get air in your brake lines, your brakes do not work as well, because if you push on the brake pedal, rather than compressing the calipers in your rotor, it just compresses the air. Okay, so let me go back to solids. So solids have set shape, set volume. And there's 2 types of solids. There's crystalline and there is amorphous. So crystalline means a regular pattern, and amorphous means irregular pattern, not regular pattern. And let me zoom in here. So all of these that were shown are crystalline. So we have a diamond, it's very crystalline, has the zinc blende structure, and it looks like that the solid matter in the Erlenmeyer flask on the left has a simple cubic. So, and you can see that liquid matter, it's not as organized as solid, but then the atoms are still pretty close to atoms and our molecules are very close together. And you have gas, matter, and it's just all over the place. So solid and liquid, these are also known as the condensed phases, and gas phase is also known as the vapor phase. So generally speaking, there is much more matter in solid and liquid. And an easy example, so gas, like air is a gas. You can wave your arms in air pretty easily. Try waving your arms underwater. So if you're underwater and you wave your arms, it's much harder. Why is it much harder? Well, because there's about 1,000 times more matter you have to push out of the way in liquid water than you do in air. And that's just because the condensed phases, generally speaking, tend to be much more dense. And I keep on using like generally speaking, because Venus, for instance, has a surface pressure about 100 times that of the Earth, and I don't know what it'd be like to move your arms on the surface of Venus. I mean, I imagine it's harder. Well, it's got to be harder than the Earth. I don't know if it'll feel like you're underwater or something, but anyways, yeah. So, but generally speaking, condensed phases much more. So, although we've seen these two pictures, and you're like, oh, so matter must be very crystalline. No, matter's not very crystalline. It's generally just a jumbled up kind of uh, conglomerate of atoms and molecules. There's holes missing. There's points of the surface that are missing. There's a crystal structure in one point. It grows a little bit, but then it's joined by another point, and the joint is also a little different. So it's it tends not to be crystalline. Okay, so still changing topics yet again. Let's talk about matter. So we're going to talk about matter, and matter is defined by something that has mass and takes up space. Mass is the amount of matter, and volume is how much space it has. So matter is something that has mass and volume. So let me talk about this in the most general, and then we'll go to specific. Then I'll tell you bottom up. So I'll tell you both ways. So the most general way of looking at things are mixtures. Most everything we see are mixtures. So and specifically heterogeneous mixtures, or sometimes called heterogeneous. I say heterogeneous. So the beach is a heterogeneous mixture. It's not uniform. So pizza is a heterogeneous mixture. Then you have homogeneous, sometimes called homogeneous. I kind of use them interchangeably. Homogeneous or homogeneous mixtures, that means uniform. So if you look at that T there, the picture of T on the far right, that is a mixture that is uniform. The T is the same on the top, the same on the bottom. Look at a heterogeneous mixture. So pizza. Pizza is a heterogeneous mixture. Is the pizza the same throughout? The answer is no. You can have cheese pizza. Maybe you'll have a slice of pepperoni. You have the sauce. You have the crust, right? So it's different. So, but you can take heterogeneous mixtures and you can break it apart into homogeneous mixtures. So milk, for instance, milk from a cow, if you've ever seen milk from a cow, it is a heterogeneous mixture. Specifically, cream and sugar, not cream and sugar, cream and milk separate. So you put in a cow, I've never personally milked a cow, but I've seen milk that's come from a cow, and the cream floats on the top. So it's not uniform. When you buy milk in the store, it usually says pasteurized and homogenized. So homogenized milk. So that is different than fresh milk. So then you have homogeneous mixture. So homogenized milk. Then you can break a homogeneous mixture into pure substances. So milk, for instance, contains water. It contains calcium phosphate. It contains proteins like whey, right? So it has pure substances in there. And everything I've mentioned there, they're all compounds. So I even use water. Water is a compound. It is a combination of elements. So a combination of elements. Whey protein, that's going to be a combination of carbon, hydrogen, oxygen, nitrogen, and sulfur. So it's a compound of those elements. So, and then a compound you can break apart into elements. And how many elements are there? There are 118 elements that we know of right now. Of particular interest, there tends to be on the order of 90-ish on the Earth naturally. So why am I using the word ish? Some of them are short-lived. So, if you can argue whether or not plutonium, neptunium, promethium, and technetium are found in the Earth. Darlene Hoffman, she's a scientist, she found plutonium in nature. There's something called the Oklo reactor. It was a nuclear reactor that's a natural nuclear reactor. That probably made some plutonium. So it's an argument if plutonium is natural or not. There's a very, very small amount of natural plutonium, if anything. So it's kind of like on the order of 90, 88, and 92, maybe 94, but 90-ish elements that are found on the Earth naturally. So, anyways, let's go with like 118 elements. I mean, so the rest of them we can make in particle accelerators. Like, that's not a lot of elements. Well, look at this another way. So, how many letters are there in the English alphabet? There's 26, right? So, 26 letters. And how many words can you make with those letters? How many stories can you use with those words? It's infinite, right? So, and well, maybe not necessarily the combinations of them, but the stories for sure. Let's say instead of 26, let's say we had 118 letters of the English alphabet. So let's say we had a language that was 118 letters. That's chemistry. That's the answer is what language is that? That is the language of chemistry. And there's similar things. So with English, right, the T and the H, those are two letters. If you put them together, they form a new sound. The T, H of T and H, and a Th sound from TH. Same thing is true with elements. So a large number, maybe as high as a third, I don't know the exact number, but a large number of people are allergic to the metal nickel. And I'm not, but I got braces later in life. And I was talking because I'm a nerd and I like science and elements and stuff like that. I was asking my orthodontist what metal the braces were made of, and he said, "Oh, it's an alloy of nickel and titanium." And I said, "Well, do you ever get people that have allergies to the nickel?" He's like, "Nope. Nickel and titanium together, everyone tolerates." So nickel and titanium together is different than just nickel. The properties of nickel have changed now. So just like the letters T and H change when they're put together. So that's some of the great things about science, right? Okay, so Lisa specific. So we have heterogeneous mixtures, which are non-uniform. You can break those into uniform mixtures. So like milk from a cow, you can break into cream and milk. And then you can take the cream and the milk and you can break them into pure substances. And those pure substances are either elements or compounds. For milk and cream, they're all compounds. And then you can break the compounds into their specific elements. So you can have mixtures of things that are just two elements. So you can have a heterogeneous mixture of iron and nickel. So meteorites, there's certain types of metallic meteorites that are made of iron and nickel, and they have two phases. So a little bit of iron into a lot of nickel, and a little bit of nickel into a lot of iron. There's two phases that you see in these meteorites, and it is a heterogeneous mixture containing two elements, right? And you can take that and you can actually break it apart into a homogeneous mixture, a solution, an alloy of nickel and iron, and that would be a uniform solution of either the iron and nickel or nickel and iron, and that would be a homogeneous solution made of just two elements. So those are less common, of course, but you tend to have everything made from compounds. Uh, okay, and so let's break it back down the other way. So you have elements. We have 118 of them. We can combine those 118 elements to form different compounds. And then some of those compounds will mix together uniformly. Those are homogeneous mixtures. Some of those do not mix together uniformly, and those will form heterogeneous mixtures. Or we can take homogeneous mixtures that do not mix together, things like olive oil and vinegar, and then those will form heterogeneous mixtures if you put them together. So, okay. And elements, let's go back to them. We have 118 of them. So let's say we have an element, so a big, long carbon rod, and we break the carbon rod in half, and then I take that smaller piece and I break that in half, and the smaller piece break that in half. I keep on going. If I get to a point where if I break it in half, it changes the element, that point is known as an atom. So an atom is the smallest unit of an element. And carbon, yes, you can break it apart. You could break it apart into lithium, for instance. You can take one carbon atom, you can break it apart into two lithium atoms. So that is possible, but doing so, you change the element. So a single carbon atom is the ultimate particle of an element. Okay. So, and again, changing topics. So chapter 1 stuff. Physical property. A physical property is something you can find out without a substance change. So right now you can't see me. I know it on the camera, my computer on, but I'm wearing a black t-shirt. Okay, so the fact that my t-shirt is black, you can observe that without changing what the t-shirt is. My t-shirt is also flammable. So, but if I catch my shirt on fire, it is no longer a t-shirt. It has now become smoke and ash and vapor, right? So I've changed that t-shirt. So that is a chemical property. So chemical properties deal with composition changes or lack thereof. So physical properties, these are things like color, magnetism, boiling point, and so on. So phase change and boiling point, water, if you boil water, form steam, it's still water. It's just one is a liquid phase, one is a vapor phase. Changes of state are not a change in substance. And chemical properties, so if it deals with composition change or lack thereof. So gold, for instance, is a very unreactive metal. And because of that, that's the reason why we give it as gifts for things. So with our culture, putting something around your finger is a remembrance of something. Specifically, wedding rings is a remembrance of your promise to wed. What if what if you go to your girlfriend or potential partner saying, I'm just thinking, excuse my heteronormality, if you will. What if you go to your partner and say, hey, my love for you is strong as iron, and I want to present you with this iron ring as a symbol of my love. And why is this funny? Why would an iron ring be funny? Because iron rusts. So iron rusts, it chemically breaks down. So we use metals that don't corrode, things like gold or silver or platinum, right? So these things do not corrode. So we pick our rings based off of chemical properties. It's not value. Indium is more expensive than gold. Really expensive is weapons grade plutonium. So why wouldn't super rich people say, hey, I'm going to give my partner a ring made of weapons grade plutonium to show that person how much I care, because it's so expensive. Of course, plutonium is poisonous, right? But even then, people are like, I don't want that ring. I want my gold. I want my platinum. So and diamonds, we've always thought diamonds were magical too because of the high thermal conductivity. So diamonds were magical because if you touch them, they feel cold because it takes the heat away from you really quickly. Of course, if you hold it long enough, it will equilibrate to your temperature. But if you just initially, as long as the ambient temperature is lower than your body temperature, or especially your hand temperature, or your tongue, that's what a lot of people do is they put diamonds on their tongue, like big hunks of diamonds. They put them on your tongue, like, wow, that rock is cold. And that's also why they call it ice, because it's a magic rock that's always cold. So, but yeah, we have some of these magic things like gold that does not tarnish, and magic rocks that are always feel cold, diamonds. We said, hey, there's something special about these, but we pick them based off their chemical properties. Well, I guess the thermal conductivity of diamond is technically a physical property, but that's why we thought they're magical. Okay, so let's look at some of these things. So physical change versus chemical change. So here is dry ice. So it's solid carbon dioxide going to vapor carbon dioxide. That is a physical change only. And sugar dissolving. So when you put sugar in water, the sugar dissolves. But this is a physical change only. You're not changing the sugar. You're not changing the water. In the bottom here, you have propane burning. Propane is burned to form carbon dioxide and water. That is a chemical change. It is no longer propane. So the top one, carbon dioxide, subliming. This is still carbon dioxide. Sugar dissolving water. It is still sugar. And then burning propane. It is no longer propane. This is a chemical change. Change of substance. And that's what's here. Any change in state or appearance. Chemical change, the change in composition. So let's look at an example here. So what, different whether each change is physical or chemical, what kind of property, chemical, physical, is demonstrated in each case. So evaporation of rubbing alcohol. This is a chemical change. I'm sorry, this is a physical change only. This is just a change in state. Burning of lamp oil. This is a chemical change. So we are turning lamp oil, which is usually hydrocarbons, changing to carbon dioxide and water. Bleaching of hair with hydrogen peroxide. This is a chemical change. We are reacting the hair. Usually, well, this usually absorbs carbon dioxide from the atmosphere, and then that lightens the hair. Typically, is how hydrogen peroxide works. And then the formation of frost on a cold night. This is of course in Hawaii. Well, I guess it can get cold. I guess up high in the mountains. So frost forming. This is the deposition of water vapor to ice, to solid water, and that is a physical change only. So that is a physical change only, physical property. Okay. Again, changing topics. So if you need to pause and get a break, I'm going to keep on talking, but if you need a break, go and grab a drink of water and come back. Feel free to. All right, so energy. Energy is defined by the capacity to do work. There's other definitions of energy. So energy, the best definition is a physics one. It's this one. It's the integral of force dot ds, like this. This is the force along a path length, and that is the best definition. But that's also a more advanced definition. In chemistry class right now, we are just calling energy the capacity to do work, right? So my nieces and nephews, I spent some time with them in the summer, and they got lots of energy. They're always running around doing stuff. But are they doing any work? No, there's kids. They're playing. But could they, do the dishes, clean their rooms? Yes, they could. But they have the capacity to do it. That's their energy. It's the capacity. They could do work. So we have a couple forms of energy. We have potential energy, which is stored energy. Energy can be stored gravitationally. So if you have a rock at the top of a hill and you roll a rock to the bottom of the hill, the rock as it's rolling, it's turning its gravitational potential energy into kinetic energy. Kinetic energy is the energy of motion. And there's also radiation energy. So that's energy and light. We'll talk about that much more in a later chapter. But so potential energy and stored energy, also referred to as chemical potential energy. And I can say energy. What type of energy is chemical energy? It is potential energy. So the donut that you're eating, the energy you get from your donut is stored potential energy. And then you can take that energy and you can do things with it. So although it has thermal energy there, thermal energy is actually also is kinetic energy. So heat and thermal energy is kinetic energy. It is the energy of motion. So a higher temperature means that the atoms and or molecules of whatever it is you're looking at have more motion. So that is so at absolute zero, this is when all, we'll learn about translational energy later, but it's all motion, specifically translational motion, stops. So absolute zero, you cannot get colder than not moving. So that's absolute zero. And then rising in temperature, the atoms and or molecules, molecules are made of atoms, but they move faster. Higher temperature means more motion. And this is just me. It's not in the textbook, but I like talking about the four fundamental forces, and I listed 5 there. Yes, I know. 4 fundamental forces, because I'm a physical chemist, but gravity, electromagnetic, sometimes called electrostatic, nuclear weak, nuclear strong, and dark energy. So we've used the word 4 fundamental forces. Some people argue 3, some people argue 5. So gravity is the ever positive force. It exists between both matter and antimatter, and it is the weakest force, and is the attraction between all particles of matter, and this force is shared with antimatter. What is antimatter? Antimatter is the same as matter, but it has a different handedness of spin and opposite charge. So we don't really see or interact with antimatter very frequently at all. Uh, then electromagnetic. So this is electromagnetism. So electric field, positive or unlike charges attract and like charges repel. And magnetic is similar to electronic, but it's perpendicular to it. So you when you put an electron in an electronic field, it moves towards or away, so it'll move towards a positive charge, away from a negative charge in a straight line. If you put a magnetic field in an electron, it will spin. So because it's perpendicular to the magnetic force. But that's for different upcoming courses. You study more physics. So chemistry is really all about the electromagnetic force. So if you want to argue chemistry is just a subset of physics that really looks more in depth the electromagnetic or the electrostatic force. And that's what we're going to talk about mostly in chemistry is this, and not necessarily the electromagnetic force, but that's what the rules that govern it. It's so we have a positive nucleus and a negative electronic cloud, and that has certain consequences of that. So, but we'll talk more about that later. What is nuclear weak and nuclear strong? So atoms are made of protons, neutrons, and electrons, and the protons and neutrons are made of smaller particles called quarks. And the nuclear weak force is the force that binds the quarks together to form protons and neutrons. Now, so turns out the nuclear weak force is actually electrostatic. So you can argue that there is no such thing as a nuclear weak force. Nuclear strong force, this is the force that holds the nucleus together. So protons are positively charged, and they have an attraction for each other. And that force has to be stronger than the electrostatic force that wants to break them apart. And that force we call the nuclear strong force. So, and that's what binds the nucleus together. Neutrons have it too, but neutrons are neutral charged. They don't repel each other, but they act like glue in the nucleus. So, nuclear strong force. And the last one is dark energy. This is something that we do not understand whatsoever. The dark energy, the universe seems to be accelerating. Actually, the universe has undulated in terms of expansion. But dark energy, the universe seems to be expanding at a faster rate, which would suggest there's an external force being applied to it. We don't know what this force is, so we give it its own category. So, and it's dark because we have no idea what it is. Just like dark matter, we don't know what dark matter is. We see gravitation effects somewhere, but we can't find any matter, so we say it's dark matter. And dark energy, we see a force applied, but we don't know what the force is, so we call it dark. So that's our understanding. So those are the four fundamental forces. You could argue 3 to 5, but they're right there. And like I said, chemistry is all about the electromagnetic force. Electromagnetic, electrostatic, whatever you want to say. Okay, changing topics yet again. Don't you love this first chapter? Okay, so we have here, and many people that take my classes, not everyone, but many people who are here are born and raised in the United States, and we have a different system than most. We have the imperial system. In science is used as the metric system. And the metric system, we start with base units, and the rest are derived. So here is the base units of the metric system. We have the length of a meter, and mass is kilogram. Time is the second. Temperature is Kelvin. Amount is mole. The current is ampere. And the luminous intensity is candela. Okay, so candela we typically don't use anymore. We've gotten rid of that. We tend to use watts or joules, use energy for light now. So we look at light as energy instead of brightness. But let's talk about that. At least everyone agrees on the second, right? That's one thing that time we all seem to be okay with. We're okay with seconds, minutes, hours, days, years. Right? Can you imagine what the world would be like if we had different time systems in different places? But we all agree on the seconds. And thank the Babylonians for that because they like their 60s. So 60 seconds, 60 minutes. So, but anyways, time, and we actually have the meter and the second are now defined kind of interchangeably with each other. Uh, a meter is defined by how fast light goes in a certain amount of time. These may change. Right now, the kilogram is a hunk of platinum, and the problem is we have several hunks of platinum, and they have different masses, and they're getting lighter. They're starting to evaporate. So we may change the definition of kilogram. We actually might also change the definition of mole. So originally, many of these were based off of water. So a so a meter, a cubic meter is 1,000 liters. So cubic deciliter, cubic decimeter, 1/10 of a meter. So cubic decimeter is a liter of water, and a liter of water has a mass of a kilogram. And I'm using the word mass. Mass is the amount of matter. You frequently hear on Earth, we say mass and weight interchangeably. Weight is a force. So if you the mass of a kilogram in Earth's gravity has a force of about 10 newtons. At least it's so like 9.8 newtons. That's actually its weight. Weight is in newtons. But in pounds, we're used to using pounds. Pound is a force. So saying your weight is a certain, that's correct. Your weight is a certain amount of pounds. We also say a pound mass and a pound force. So here on Earth, the pound mass and the pound force are the same. At least standing still, it's the same. If you're going up and down in an elevator or something like that, your weight can change depending on the direction. But mass, so if you have a mass of 50 kilograms on Earth, and that's a weight of, let's see here, about 110 pounds. So if you have a mass of 50 kilograms, that means your weight is about 110 pounds. If you go up into space, your mass is still 50 kilograms. It does not change. Your weight, you can be weightless or appear weightless. So you have no weight, but your mass does not change. So you go to the moon, and the moon's gravity is about 1/6 that of the Earth. So if you have, I should be able to do math faster in my head. Let's see here, 50 kilograms, whatever. So the mass of you, if you're 50 kilograms on the moon, that's still going to be 50 kilograms at your weight. So let's see here, 1/6. It's not going to be 20 pounds. So let's see here, 120. It's going to be about 18 pounds. So if you weigh 110 pounds on the Earth, you go to the moon, your weight's going to be about 18 pounds. So that's a good weight loss plan, right? So you go to the moon and you're 1/6 your mass, or 1/6 your weight. Okay, so let's talk more about these units. And I told you they're going to change. The proposal right now is to change the mole and the kilogram to silicon. Right now, the kilogram is a hunk of platinum, and the mole, so 12 grams of carbon-12 is a mole of carbon. That's what it's based off of, is exactly 1 mole. The argument now is to have a sphere of silicon be the kilogram and the mole, because kilogram has only one, or because silicon has only one isotope, at least that we see it in here. On Earth. So gold is similar, but I guess aluminum is too. But we've picked silicon. Oh, that's Earth. So we're thinking about changing it. So that hasn't changed yet. So right now the kilogram is still a hunk of platinum, and the mole is still a base of carbon-12. But this might change in the future. Okay, and then the rest of the units are derived. So I mentioned, and you don't have to know this for this class, but I'm just telling you so you understand. So so let's talk about force. Force is mass times acceleration. So a Newton, for instance, 1 Newton, I mentioned that before. It's mass times acceleration. Acceleration is going to be, so a meter, and it's the second derivative, so it's time divided by time squared, and then mass. So a 1 Newton is a kilogram times a meter per second squared. So that's a Newton. And a joule is a Newton meter. So 1 joule is a Newton meter. That's a kilogram meter squared per second squared. Okay, so the word joule is that. And a watt, so 1 watt is a joule per second. That's going to be a kilogram meter squared per second cubed. So mass times length squared divided by time cubed is power. So you can learn more about this in physics class, but I'm only telling you this now so you understand that other units are based off of these base units and then derived from them. Okay, and let's talk more about some of these units, and let's talk about density. Density is defined as mass divided by volume, or I read this equation, density is mass divided by m over v, mass divided by volume. And density is an example of something called an intensive property. So it is independent of the amount of substance. So if you have a drop of water, what's the density versus a glass of water versus a big lake of water? What is the density of water? Does it change? No. Does the mass of the water change? Yes. Mass is an extensive property. This depends on the amount of something. So there are many types of intensive properties, so not just density. Things like conductivity, for instance. So, and there's other extensive property. Volume is another one. So, right, the more stuff you have, the bigger the volume. Okay, so let's go over an example here. With density. So a man receives a platinum ring from his fiance. Lucky fellow. He notices that the ring feels lighter from its size, and he takes a balance, and so let's see, mass density. So it has a mass of 3.15 grams, and notice that the ring displaces 0.233 cubic centimeters or milliliters of water. Is the ring made of platinum? So look at the density. Density is mass divided by volume, and he found out that this ring was 13.5 grams per cubic centimeter. And that is much too low to be platinum. Platinum is around 21.4. So unfortunately, this unfortunate fellow was given a not platinum ring from fiance, or the ring was swapped out with something else. So, alrighty. So you understand that this is, and this one I'm not kind of going through. I can go through them on my iPad, but I'm just, this one is pretty straightforward. Okay. All right. So again, changing topics. Significant figures. So certain measurements mean more or less. So when the astronauts went to the moon, for instance, we placed some mirrors on the moon, and a couple times a day we check the distance between the Earth and the moon using lasers and these mirrors. Okay, and we found out from this that the moon is slowly moving away from the Earth on the order of about 2 centimeters a year. Okay, so now from that you can say, well, this must be a very accurate measurement of distance. 2 centimeters is not very big at all. And if you look at my car, I have an odometer, and the odometer works to the 10th of a mile. So I could use something like an odometer. If I want to know the distance between my house and Foodland, I can use my car's odometer to do that. That's probably what I do. Or I would use my step tracker on my cell phone or something like that, because it tells me how far I've walked. Those are ways of measuring distance. They're not super accurate, but they work. They work within reason. And then you have like the laser sight that we use for the moon, right? So that's very, very exact. So, well, how do we tell the difference? How do we know how well we know something? And the answer for that is significant figures. So significant figures, this is our way of knowing how exact we know something. And some things we need to know very, very precisely. Some things we don't need to. So let me give you an example. Say I'm making chocolate. Okay, I'm making chocolate and I need to have a certain concentration of sugar in the chocolate. And let's say as I'm making the chocolate, I trip and I drop a little bit of sugar on the ground. And like, meh, I keep on going. I'd probably, yeah, I like to think I wouldn't pick it off the floor and put it in the chocolate, but let's just say I'll leave it on the floor, and I pour it into the chocolate machine. So that's not a big deal, and the chocolate probably come out fine. Let's say I'm making IV bags for someone, and let's say I have a factory that makes IV bags, and then what happens if my concentration of sugar or my concentration of salt is slightly off? People can die, right? So that's an example of something I need much stronger controls if I'm making IV bags versus if I'm making candy, right? So because of that, we have much harsher, much more uh, uh, well, precise and accurate measurements, much more equipment for certain processes, right? Because sometimes you need it, sometimes you don't. And okay, so generally speaking, measurements are reported so that every digit is certain except for the last. So, and written here, same as in the textbook. So, like the 5.213, whatever this is, grams of sugar. The last term is an estimate. It could be, we're not entirely sure, but the last one we're certain about these other ones. So, let me give you an example here. Now let's look at this meniscus. So meniscus, when you go to the lab, you'll notice that water, especially for silica glass. So this is, borosilicate is what Pyrex is. That's what most glassware is. But there's an attraction between the water and the silica. And because of that attraction, it brings the water up a little bit. We measure from the bottom of the meniscus in class. And you can kind of see it's right here is where the measurement is. And what is this? What is the volume of this? And we can say it's 4 milliliters, and this is 0.5. And you can kind of see here, it's between 4.5 and 4.6, but it's closer to 4.6. So I'd say it's like 4.5. I'd say 8 or 7. I'll say 8. And then this is typically, for this, it's plus or minus about 0.01. Because you're unsure about that. It could be as high as 0.02. But the point is, we don't really know about that last digit. That 8 is uncertain in that. So what does the book say? It is 4.57. What if you, okay. It's estimated. I thought it was 4.58. So, I mean, that's the point. The last digit there's an estimation. We definitely know it's at least 4.5, but the last digit not so sure. So, and here is the thermometer. This one's a little harder to read because where is the end there? It looks like it's a little bit past the 100 mark. So it's probably up around here. So there's 100 and 1, 2, 3. Wait a second. This is 1, 2. This is a little over 103. I'd say 103.1 or something. I'd say this is 103.1. I'm assuming it's degrees Celsius. It doesn't give the scale. It could be Fahrenheit. I don't know. But then again, there's some error with that last digit there. We are uncertain. So, okay, but let's talk a little bit more about significant figures and how to tell them. So here are the rules. See if you can. So all non-zero digits are significant. Interior zeros are significant. Leading zeros are not significant. Tailing zeros are categorized as follow. Tailing zeros after decimal point are always significant. Before decimal points are always significant. And trailing zeros before an implied decimal point are ambiguous and should be avoided. So, and this tailing zeros, this is the implied of that. They actually, I don't know, it's on the internet, so it must be true. They actually uh, did not report the proper height of Mount Everest, apparently, because like I said, the internet must be true, because it did have a bunch of zeros on it. So they found it to be an exact something, so they added another 2 feet on it or something like that to make it look like it was not an estimate. But okay, alrighty. So let's start with rule number one. All non-zero digits are significant. Um, so this first one here, this one has 4 sig figs, significant figures. So this zero counts. And also trailing this one here, trailing this has 3 sig figs. So this middle one here, 408, that has 3. This number right here has 1, 2, 3, 4, 5. That has 5 sig figs. Okay, hopefully you can see how I'm doing this. And then leading zeros, so for 0.0032, this has 2 sig figs. Those are not significant, just like the trailing ones right here. That's not significant. After a decimal point, these are always significant, so these things here listed, those are significant. And the ones in the middle, those are significant. If you see the word 1200 here reported, you might say that's got 2 sig figs. It's ambiguous. If you report it this way, you know that there's 4. If there's a decimal point after it like that, and I don't know if it's the period at the end, that's saying that it's just 4. So it depends. Common in some textbooks. It depends because notation changes over time. So we don't always use the same notation. Okay, and then there's exact numbers. Exact numbers have an infinite number of significant figures. So 3 atoms means that the 3 just means infinite. It doesn't mean there's 1 sig fig and 3 atoms. It means it's exact. And there's 100 centimeters in a meter. But that's also an exact number. That's a definition. So, and using equations, so like the radius is the half of the diameter divided by 2. 2 is the exact number. So it's the measurements. The measurements are the ones you have to worry. And then so let's say the person has 3 fingers on his right hand. I know that's a measurement, but that's still considered a whole number and has an infinite number of significant figures. Okay, and let's determine the number of sig figs in each of these numbers. So this number here, it has 1, 2, 3, 4. A has 4 sig figs. And these 2 here are not considered sig figs. This for B, 1, 2, 3, 4, 5 sig figs. The middle zeros are considered significant figures, so that's 5. So definition of decimeter, this has infinite. That's all an exact number. This one here, this has 1, 2, 3, 4. That has 4 sig figs. So the zeros after the decimal point define that. And this one here, these zeros do not count. This one has 1 sig fig. And F, this is ambiguous. This is a hard one. Most people would say that has 1 sig fig. So, but you could argue that it has as much as 5, but usually you would see it as 1.0000 times 10 to the 5 meters, if it was in fact 5. But that looks like it's 1. It's ambiguous. So, all right. Now let's move on and talk about calculations. Whew, long chapter. I'm getting tired. All right, so multiplication. When you do multiplication, you perform the function and then you round at the end. And so always do this, and this is to avoid something called truncation error. So multiplication and division, look at the final answer and then and then adjust the final answer based off of that. So multiplication, division, look at the final answer, and bring it to the lowest number of sig figs. So in the first example here, there's 4 sig figs times 5 sig figs times 2 sig figs. We get an answer, and then we round that answer to 2 sig figs because of this one here. That the one's limiting our knowledge. And same thing with division, go to 3 sig figs. So in addition subtraction, it goes by the lowest that you can accurately do something. So if you look at this example here, we have a measurement that we know to be 0.07, but the other ones we know further. We only know it. What about this number here? It could be different. We're only sure about that 7. So because of the uncertainty, we can only report that we know it by this much. So, okay. So, and for rounding for sig figs, you round up and down. So the usually you round up for the 5. Some books have a little different procedure that you always round to an even number. Like let's say that you had 5.25, for instance. This would say you round up to 5.3, but some of them say you round down to 2. So it depends on the book, but usually though we will round up. So calculators. So okay, and then the last one. So whenever you round with errors, so I mentioned something called a truncation error. Don't sequentially round your answers. Round it at the end for this. Your calculators actually, Excel does this. Your calculators do it. There is some truncation error in your calculator and in like Microsoft Excel with spreadsheets, but because they round because they just keep a certain number of digits, but when you're doing a calculation and you know it's 2 sig figs, do the rounding at the end. That's the point of this. So I know that this one here, if you're looking, this confused me when I was reading the book. It's like, this has 3 sig figs. Right? So why am I doing that? It's probably like, why don't I call this 19.2? That's because it was telling you to round it to 2 sig figs. The idea is that you round it at the end, not sequentially. Okay, let's do an example of these. So let's do the calculations to the right number of significant figures. So if you go and do this, so this, don't forget the order of operations. Order of operations, so I guess I do order of operations. This is, I should back up. So you have first, you have the parentheses. Seconds, you have logs and exponents. Third, you have division and multiplication. And fourth, you have addition and subtraction. And you also go left to right. So left to right when you do this. So most of the mistakes I see on students making is actually order of operations. So if you were to do part A, just go left to right. And then if you do that, you will get this answer to be, this will be 0.65, the 5 looks ugly, 5219. So then you look at this. This has 3 sig figs. This one has 4. This one has 5. This one has 5. So we know it to 3. So since we know it to 3, this is going to be 0.652. That we know that, at least because of the significant figure argument. Now for this one here, so let's move on to B. These ones you just straight in. So 0.355 plus 105.1 subtract 100. 0.58. If you do that, you get this to be 4.8730. Now the point though is we only know to here. Then you might think, oh, I'm going to round it up to 4.9. We only know about that one there, so you probably can even toss these digits here anyways if you want. We're not entirely sure. So the answer, oops, sorry, I moved that. The answer here is going to be 4.8. You truncate it, and that you just truncate, you chop right to those last two because of that one there. And okay, so for part C, the way you do this one is you start here and you do, so this is in parentheses here, you do this one first. So looking at doing this one first, you get this number to be 0.344. Oh shoot. That middle one is going to be 0.3455. Okay, and this one, it's usually advised, I mean, this one, although because of here, there's only two significant figures in this calculation, usually you keep on going around at the end. So then now when you have this, you can then do the rest, and the whole thing is going to end up being 52.79904 if you carry it all out. And then with the sig figs, this is 53. So again, do this one first because it's in the parentheses, and this subtraction, the parentheses, has two sig figs, and then when you do your calculation at the end, round it to two sig figs. And well, this one here for D, you wouldn't even have to put this in parentheses because multiplication happens before addition anyways, so that doesn't really matter. So if you do the multiplication for D, this is going to be 0.142 minus 8.02, and then this is going to, oh wait a second, I got that wrong. I'm looking at the textbook. That's the answer. I got the wrong answer. This is going to be 8.162 minus that, and you get 0.142. And how far do we know this? So let's see here. We have two sig figs here. So, but we only, so we have two sig figs here. And from this, let's see here. One decimal place. So, okay, because this calculation, this one right here, we know that, let me change the colors here. We only know those two sig figs there. Because of this calculation, the 14.84 times 0.55, that gives us two sig figs. So because of that, we only are certain of those two sig figs, which means we're only certain down to the 0.1. And then when we subtract that there, we can only say that this is 0.1 for this answer. So this one's a little more tricky, this one. So I gotta be careful with this one here. So the multiplication happens in parentheses. That has 2 sig figs, which means we know it down to the 10th place of the decimal point. And then when we subtract that, we are only sure the answer down to the 10th place. So that means it's going to be 0.1. Okay, so recap with this one. So the first one here, we have multiplication straight through, multiplication division straight through. And then we just go by the lowest number of sig figs there in part A, which is 1.10 to 3, so rounded to 3 sig figs. For part B, we have addition and subtraction. And we truncate that one based off of we know to the 10th place there. For part C, we have multiplication and a division of a quantity. We do the quantity first, and the quantity we know down to the 10th place. So, and that answer there will give us 2 sig figs. If it was different, if it wasn't 452 for both, let's say one was say the first one was 500, we would have more sig figs. So that would change that. But we only know down for that, we lose sig figs on that calculation. And then when you multiply it through, you have to round it to the 2 sig figs based off of the sig figs of the parentheses quantity. And same thing with D. The calculation, the parentheses quantity, has 2 sig figs, which means that you know that number to the 10th place, and when you subtract it from the other one, we're only certain of that answer down to the 10th place. Okay, and here are the order of operations. Again, that's the most common mistakes that I see with students, just following that. Okay, so moving on, general problem solving. So when you solve problems, chemistry class and other, and this works for more than just this class. So you start off by sort. Look at the information is what you're given, and then see what you're asked for. I mean, don't just look at something and start going for it. You have to figure out what you know and where you're going to go, and strategize what you're going to, and then you got to figure out how you're going to get to the problem. Then you solve it, and then you check it. And the way you check things is you can. Part of it is, does the answer make sense? It's kind of like maybe you've done a calculation and you've gone and seen your teacher, and the teacher says, doesn't that calculation make sense? You're like, what do you mean does it make sense? I did the calculation. I'm like, yeah, does it mean anything though? Like if you calculate out the mass of a sodium atom to be that of the sun, then you're like, oh, maybe I made a mistake somewhere. You know, does this look like it's right? So that's what we're saying. Us teachers, I should say, we were saying. Okay. So first one here, convert yards to centimeters, and this is known as dimensional analysis. So much of this class, we use a technique called dimensional analysis. So when you do this, you have conversions. So we want to go 1.76 yards to centimeters. So what you do is you start with 1.76 yards. And then now I'm going to multiply this by 1. So, for instance, 1 meter is equal to 1.094 yards. Right? And then there are 100 centimeters in a meter. And if you notice, when we multiply these units cancel, and we are left with, when you do this, then you are left with 160.87. Okay, so but you round up. So round up for sig figs. So this is 161 centimeters. Okay, so now I'm going to, and I apologize if anyone is colorblind, I'm changing colors just so you can see it because I'm using both at the same time. I showed you there, these are fractions. And what you're doing here, so 1.76 yards, you multiply a meter divided by 1094 yards. So 1 meter equals that exactly. So you're multiplying it by 1. You've just multiplied it by 1. That's all you've done. But let me do the next one here. 1.8 quarts to cubic centimeters. So we start, so 1.8 quarts. And I tend to use boxes. I do it for a few reasons. Number one, my undergraduate degree is in chemical engineering, so I used to use engineering paper. And my PhD, though, is in chemistry, so I am both an engineer and a chemist. But I guess the graph paper lines I got used to them. And it's nice and neat. I think to use the boxes. So we have a liter to 1.057 quarts, and then a milliliter is 10 to the minus 3, so 0.001 liters, and a milliliter and cc are the same thing. So 1 centimeter cubed to 1 milliliter. And you can drop the 1, so you can actually just drop the 1s there. And same idea, I'll use green. Quarts cancel, liters cancel, milliliters cancel, and you are left with, okay, so these are exact numbers, and their answer is going to be to 2 sig figs. So, which means with this you'll get 1703 centimeter cubed, or because I have 2 sig figs, we're only sure about that, it's 1.7 times 10 to the third centimeter cubed. Like that. Okay, so recap with this one. We're using a technique called dimensional analysis. And you're just taking what you know in the beginning, and then as long as the units cancel out, you get the answer that you want. And so how does this work for a sort? So look at the given information, for example, 1.7. We're given that we have 1.76 yards, and we need to know it in centimeters. So I got to figure out how to get between the two. And I think, okay, well, yards, actually, I'm following along the book. For me, I would, which would be an equally valid way to do it, I'd probably turn the yards into feet, the feet into inches, and an inch is 2.54 centimeters. So that'll do the same thing, right? And convert quarts to cubic centimeters. You can do this, I mean, so there's more than one way to do it, right? So same idea with quarts to cubic centimeters, you gotta convert units and then change it to SI or metric, and then get the right base unit on that. Okay. And what about units raised to a power? So you have to be careful about these with dimensional analysis. So this is also a common mistake. That's why I'm going through this right now. Displacement to the volume of a 5 centimeter. So we want to know a 5.70 liter engine into cubic inches. So we have 5.70 liters we start off with, and we're going to get to cubic inches. So how do we do this? We have to convert it. So we know probably the easiest thing to do is to turn it into cc's. So cc, cubic centimeter, and milliliters. So we have there are 1,000 milliliters in a liter, and then cubic centimeter to milliliter. And I told you before, an inch, there are oh wait, I got it on the wrong side. So there are 2.54 centimeters in an inch. Okay, so now we're halfway there, though, and we're not halfway there. The trick here is we have to cube this because of the unit cubic centimeters. So you have to cube that answer to make sure that you get the right answer. And then in doing this, so if you look at the units, right, so the liters cancel, the milliliters cancel, and now the cubic centimeters will cancel. So you have to go through it that way. And of course, if you do the calculation here, you get 347.835, and then the 3 sig figs, this is 348 cubic inches because of the 3 sig figs there. Okay, so recap for this one is the same idea as the rest I was going through, but the trick here is this step here. Make sure that you cube that to go with this cubic centimeter unit. And this is the lecture that never ends. Density as a conversion factor. The mass of fuel in a fuel jet must be calculated before a flight to ensure the jet is not too heavy to fly. A 747 is fueled with 173,231 liters of jet fuel. So what is the mass of this one? So this one's pretty straightforward, and we just want to know mass in kilograms. So this is a one-stepper, which is nice. So 173,231 liters, and you want to know the mass. So I can see where this is going. You're gonna have a middle step, but you can actually cancel it out. So liters, and we're given this in cubic centimeters. So so this is 1,000 milliliters, 1,000 cubic centimeters to a liter. I know it's a milliliter, but the same thing. And then you have 0.768 grams per cubic centimeters, and you probably want to convert it back to kilograms. Does the book do that? Let me look here. Let's see. I mean, what's the mass? It doesn't say the mass of fuel kilograms. This is a kilogram to 1,000 grams. So what's nice about this is you can just not even worry about those two steps. So they cancel out, and you don't even have to put in your calculator if you don't want to. And then when you do this, you calculate it out, and you get 1.33 times 10 to the 5th kilograms, and which is 133, so 133 tons. It's a lot of fuel. So 133 metric tons of fuel is your answer. So, man, that's a heavy jet. All right. And then why do they charge me baggage fees? Jeez. Keep my own 30 bucks in the future. All right. So one of the illustrations with this one is if you're looking at it, you can make your life easier and you can skip steps. So that's a nice thing. If not, you can just keep on going through the whole thing and you don't have to worry about it. So, all right. Ooh, this is a little more challenging. All right, now last one of the chapter. What is the radius of a spherical water droplet has a volume of 0.058 cubic centimeters? So volume of the sphere is 4/3 pi r cubed. And this is just me. I like doing the math first. So we have volume is 4/3 pi r cubed. And now we want to know the radius. So I always do the math first. So looking at, so this is going to be 3/4 volume over pi is r cubed. So I'm doing the algebra right, so I'm bringing the 3 up there, the 4 down there, the pi down there, like so, and which means then the radius is the cube root Cube root is the same thing as raising something to the 1/3 power, like so. And then you put this into your calculator. It's going to be 3 times 0.058 centimeters cubed over 4 pi. Pi is 3.14159, so on, 4 pi. And raise that to the 1/3 power. And what do you get? And if you do that, you get 0.24 centimeters. And if you notice here, the cube root will go for the math here, and then the cube root of a cubic centimeter is a centimeter. And there's, just so you know, of course, if you dig a cube root, you're going to get some imaginary results. If you're wondering, if you've gone further in math, you know that a cube root, when you do that, there are going to be 3 answers to it. The other answers are going to be imaginary, so the imaginary answers don't matter. So, of course, if I'm confusing you, don't worry about it. That's just if you go and study math further with that. But we only have to concern ourselves with the real answers, not the complex ones. And that is the answer there, 0.24 centimeters. So this is this one here. This is also a personal preference. I just find it to be cumbersome if I put the numbers in. So like if I start putting the numbers in, then I start making mistakes in my in the numbers I put in my calculator. So I prefer to do the algebra first and then put the numbers in last. So that's my own personal preference, like I said. And the other thing is, when you do these calculations, make sure you follow the proper order of operations, meaning calculate out 3 times 0.058 divided by 4 times pi. So make sure you don't, if you're going to put this in your calculator, do the quantity 4 times pi first, if you will, or you could do 3 times 0.058. Let me write this down. I used to have an app on my cell phone, but it doesn't work anymore, unfortunately. Put this in your calculator, do 3 times 0.058 divided by the quantity 4. Usually there's a pi button. If not, you can do the 3.14159. You can do that, or you can do this. Oh, then there's 0. Sorry. 0 point. I missed the 0 there. Yeah. Divided by 4 divided by pi. You can do it that way as well. That's going to give you the same answer. What you don't want to do, don't do this. So this bottom line here, that's wrong. You can do one of the top 2. That'll give you the right answer. This bottom one here, because your calculator is only as smart as the person using it. Because the calculator, when it views this bottom one, is you take 3 times 0.058, so that's going to be about like 0.18. So that's about 0.18 divided by 4. That's going to be about 0.04. Okay, and then so up into this point right here, the calculator is going to see that as 0.04, and then times pi, then it's going to be about 1.2. So it's going to look at this answer here and say this is about 1.2. Same for this one here. So what did I say? It's 0.04. This is going to look at this one here, and it's going to say it's about 0.001-ish. So just trying to do the math in my head This one's going to be in the same as this one here. That's going to be about 0.001, but this one here is going to be about 1.2. So again, I'm guesstimating it quickly in my head. Make sure you use the proper order of operations, otherwise you get the wrong answer there. So this is what I mean by a check, and then with that. So okay. And then with this to check to see, does this make sense? Well, what you can do with this answer is then you can throw it back into this equation and see if you do get this volume out. But that looks about right, though, to me. I don't think I need to check it out. Okay, so we are now done with this chapter, and I will see you for the next chapter. Goodbye for now.